So today we're going to look at the combined gas law. And combined gas law is just a way of combining all three laws that we've done. So if we look, we got Boyle's law dealing with pressure and volume. Remember that is inverse. And we have Charles' law and Gay-Lussac's law dealing with volume and temperature and pressure and temperature. Those are direct. And what we can do to simplify this is, because all three variables are related to each other in one way, shape, or form, we can combine them. And the way we do that is we multiply each side of all of the equations. So I'm going to multiply the one side of all the three equations by the two, with the two side on the other side, multiply all those, and see what we get. So when we do this, we combine like terms, so the P1s multiply, the V1s multiply, the T1s multiply, and when you do that, you end up with this. And if you notice, everything on each side is squared, so we can just get rid of the squareds if we want to just take the square root of both sides, which kind of looks like this. If you know, like if you take, like, for example, the square root of 5 squared, well, the square root of 5 squared, that's taking the square root of 25. Well, square root of 25 is 5, so the square root of 5 squared is just 5. So the square root of p squared is p, square root of v squared is v, and so on and so forth. So what ends up happening is we get this equation, which is the combined gas law. Now, what you can do is, if you look at this combined gas law, if you get rid of temperature, for example, you can see that there you have Boyle's law. If we hold, let's say, pressure constant, like so, now we have Charles's law. If we hold volume constant, now we have Gay-Lussac's law. So all three gas laws are built into this. And we can use this law to solve any question of any gas law problem that you may get. Any questions we've had where only one thing's changing can still work. So the easiest way to do this is just to look at some examples. Now, all the previous things still count. So when we start our questions, we have to make sure our units are in Celsius, our volumes are the same unit, or sorry, units are in Kelvin, our volumes are the same unit, and our pressures are in the same unit. So right away, I'm going to fix these temperatures, because this is 298 Kelvin, and this is 128 Celsius becomes 401 Kelvin. So now, what I'm going to do is write my formula. So P1 V1 over T1 equals P2 V2 over T2. And now I'm going to substitute my values in. Well, going through, this is volume, this is temperature, and this is pressure. This is temperature, this is pressure. This is 1, 1, 1. This is 2, 2. And we want to find V2. So that's what I'm going to try to find. So substitute my values in. 1.25 atmospheres times 298. We're looking for the volume here. That's 25 liters. Over 298 Kelvin equals P2, 0.75 atmospheres, times V2 we don't know, so 2, and 401 Kelvin. So now what I'm going to do is I'm going to multiply both sides by 401 Kelvin, divide both sides by 0.75 atmospheres, so if you look, these cancel, these cancel. So what we're left with is V2 equals 401 Kelvin times 1.25 atmospheres times 25 liters divided by 0.75 atmospheres times 298 Kelvin. So V2 will equal. Now when we solve this out, you must follow order operations. So you have to do the math in the numerator, then the math on the denominator, then divide. You can't just divide, punch it into the calculator the way you see it. So the way I set this up is 401 times 1.25 times 25. That's the top, so I hit enter. Then I divide by, in brackets, 0.75 times 298, but put brackets around them, so it will do the multiplication first, then divide. You should get, if you punch it in your calculator correctly, an answer of 56.0 0.07 liters. Now, it's hard to decipher sometimes whether this is going to make sense or not because you have two things changing. The temperature is rising and the pressure is falling. So that tells us actually in both cases, both of those things are going to make the volume get bigger, which it did, so that would make sense. If you're doing the logic method, we're trying to find the new volume. So I'm going to start with the original volume, and I'm going to make it bigger or smaller depending on what is happening. So let's choose one of the first changes. So let's start off with the pressure change. I'll do pressure change in red. So pressure was going down. So that should make the volume go up. So I need to make this bigger using my pressures. So 1.25 needs to go on the top, and 0.75 goes on the bottom. Now, using blue, I'm going to do the temperature change. So the temperature went up. So I'm going to write that down. Temperature went up. So to change the volume, if temperature goes up, the volume should also go up because it's a direct relationship. So now I'm going to set up my two temperatures to make the volume get bigger as well. So 401 Kelvin is on top and 298 Kelvin is on the bottom. Oops, don't need the bracket there. So when you do that math, it should end up being the exact same answer, which is 56.07 liters. There's your final answer. Sorry guys, had a little interruption there. So moving along to the next example. In this one we have actually only one thing changing. So if you look, it says that we have a fixed volume. So that means we can actually just not worry about volume because it's not going to change. So we can actually, if you want to set it up as the combined gas law, it would be P1 V1 over T1 equals P2 V2 over T2. And then so because the volume is not changing, both of these volumes will be the same and they'll end up canceling each other out. So your formula ends up just being P1 over T1 equals P2 over T2, which is Gay-Lussac's law. So now all we have to do is just substitute in our values. Before I do anything, I should be changing this to 298 Kelvin and 150 Celsius. Let's check that out really quick. So 150 plus 273 is 423 Kelvin. So 652 kPa is our initial pressure, and our initial temperature is 298. So 298 Kelvin. And our new pressure is P2. Our new temperature is 423 Kelvin. So P2, we've got to multiply both sides by 423 Kelvin. 423 Kelvin. So cancel, cancel. So we'll end up with 423 times 652 divided by 298. And I get a pressure of 925.49, and that will be in kPa. Now, if you look, the temperature went up, so the pressure should go up. That makes sense. With the logic method, there's only going to be one ratio to worry about. So we are trying to find the new pressure. So I'm going to start with my original pressure, 652 kilopascals. So the volume is constant, it's fixed. So really, you're just not changing anything. So I don't have to worry about the change in volume because no change in volume means zero change in pressure. So we'll get rid of that. Now, if we want to look at temperature, the temperature goes from 298 to 423, so temperature goes up, so the pressure has to go up. So I got to make it bigger, 423 Kelvin over 298 Kelvin, and it'll end up being the same answer, 925.49 kPa. So now, give the next two a try, come back, pause the video, come back and watch and see how you did. It'll help you a lot more if you just try it on your own and then come back and check your answers afterwards. So in doing the try these ones, I'll do both formula method and logic method. So before we do anything, let's fix these temperatures. So this should be 331 Kelvin. The new temperature we're wanting to find, so that's a question mark. It says in Celsius, we'll change it back to Celsius at the end. So I'm going to write out my formula, P1 V1 over T1 equals P2 V2 over T2. So going through the question, so that's a V1, this is a P1, this is a T1, T2 we don't know, V2 and P2 we do know. So substitute my values in. 325 kPa times 125 liters over T1 is 331 Kelvin. And then T2, we don't know, but P2 is 101.3 kPa times 22.4 liters over T2. So this is where you have to solve for T2. We got to get T2 out of the denominator. So I'm going to multiply both sides by T2. T2 cancels over here. So then I'm going to have to start rearranging. So I'm going to rewrite it. So we have T2 times 325 kPa times 125 liters over 331 Kelvin equals 101.3 kPa times 22.4 liters. Now, to solve for T2, we're going to have to get rid of 331. So I'm going to multiply by 331 Kelvin on this side. So that means I do it here. So I'm going to run out of space, but 331 Kelvin. And then I'm going to have to divide by 325 kPa. So divide by 325 kPa. And I'm going to also have to divide by 125 liters. So 125 liters. So now, if you look, what ends up happening is cancel, 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 cancel. So what you're left with is T2 equals 101.3 kPa times 22.4 liters times 331 Kelvin divided by 325 kPa, 125 liters. So T2 ends up being 18.49 Kelvin. Take away 273. Negative 254.51. And there's your final answer. If we're doing the logic method, it's the same idea. We are changing, we're trying to find what the temperature change is. So I'm going to start off by writing my temperature. So 331 Kelvin, that's my starting amount. Now our temperature, let's start off with a change in volume. So our volume changes, the volume is going down. It's going from 125 to 22.4. So volume goes down, that means the temperature should be going down. So to make the temperature go down, I have to multiply by the ratio of volumes with the smaller volume on top, so 22.4 liters, and the bigger volume on the bottom, which is 125 liters. So there's your volume ratio. And now I'm going to look at my pressure. So the pressure is going down as well, which it means the temperature's got to go down as well. So I'm going to multiply by my ratio of pressures that's going to make it get smaller. So that is 101.3 kPa over 325 kPa. And if you look on the top in this equation, we had 101.3, 22.4, and 331. That's the same. And on the bottom, we had 325 and 125. So this ends up being the exact same answer. So our final answer is 18.49 kelvins, or negative 254.51 degrees Celsius. So it's the same idea. So here's another application of this. If we have salvage divers trying to salvage something that went through the ice in the wintertime, they will use airbags. So they will put bags down into let's say it's a car that went through the ice. They'll put the airbags into the car empty. They'll pump air into it. But they don't want to pump too much because as it surfaces, the pressure and temperature are going to change, and then that will actually, the bag could burst if it gets too high. So in this case, what I'm going to do is I'm going to solve this for V2, but I'm actually just going to do logic method, because if you're doing formula method, the final calculation should end up being the same. So at the bottom of the lake, it has 145 liters at a temperature of 5.2. So 5.2 degrees Celsius will be, I'm going to write this in here, 278.2 kelvins. And the pressure is 6 atm. So this is going to be V1, this is T1, and this is P1. As the bag comes to the surface, the pressure is only 1 atmosphere, so that's P2. The temperature is 16 Celsius, so that ends up being 289 Kelvin, so this is T2. And we want to find out how big this bag is going to become as it surfaces, because the pressure is dropping and the temperature is rising as it comes up to the surface. So start off with what we have. We have our volume, so 145 liters. And we're going to change this volume based on our temperature changes and our pressure changes. So as the bag, let's look at temperature first. As the bag comes to the surface, it starts off at 5.2 Celsius, it ends up at 16. So the temperature is rising. This is going to make the volume rise. So our ratio for that, to make the volume get bigger, I want the bigger temperature on the top. So 289 Kelvin is on the top and 278 Kelvin is on the bottom. 278.2, I should say. Now, that's our first ratio. Now, the second change is where the pressure is changing. The pressure is actually going to decrease. So the pressure starts off at 6 atmospheres and becomes 1 atmosphere. It's actually 6 times less. So that means when the volume is going to increase by a factor of 6. So I want to make the volume bigger. 6 atmospheres goes on top, and 1 atmosphere goes on the bottom. So here's our second ratio. So I'm basically multiplying across the top, 145 times 289 times 6. And now I'm going to divide by the multiplication of the bottom. So 278.2 times 1, which is basically 278.2. So I get a volume of 903.45 liters. And it can only hold 750, so therefore, bag will burst. And that's how you would solve this using logic method or ratio method. Now, if you were doing formula method, you would have these 3 numbers on the top and these 2 numbers on the bottom at the end when you're solving for your final volume, your V2.